Welcome to Math Table. Today we will review and practice the notion of continuous. So let f of x be a function defined at all numbers. Write what it means for f to be continuous at a. Pause the video. Continuous. A function f is said to be continuous at a point a if the limit of the function f of x as x approaches a is equal to the value of the function f at the point a, that is to say f of a. Now let's make a few comments. Here's an equivalent definition. F is continuous at the point x now if as h goes to 0, f of x plus h is equal to f of x. Let's understand how this is the same. So instead of approaching the point a, we're going to approach the point x. So we want the value at f of x. Now, what does x plus h mean if h is going to 0? Well, as h goes to 0, x plus h is going towards x. So what we're looking at is, on this side, the limit of f as we are going towards x. Now, a note here is that the discussion requires that the function is defined on an open interval which contains the point a. So if we have a function that looks like this, we cannot discuss continuity of the function at this point because this function is not defined on this open interval that contains this point. Lastly, a function is said to be continuous if it is continuous at every point in its domain. Which of the following plots represent functions that are continuous at x equals 0? In this first example, say this function is f, the value of f at 0 is indeed 0 right here. However, the limit as x approaches 0 from the left of f of x is 0, but the limit as x approaches 0 from the right of f of x is -1. As a result, this limit does not exist. Since does not exist is not a number, it cannot equal the number 0. In our next example, clearly as you follow this function down here, we're heading towards -1, and here we're heading towards -1. So the limit as x approaches 0 is -1, but the value of the function at x equals 0 is 0. This is again an example of a function that's not continuous at x equals 0. Here in this example, we do not discuss continuity at x equals 0, simply because the function is not defined at x equals 0. We could say, strictly speaking, that this is a continuous function on its domain of definition. Here, we now extended the domain of definition to include the point 0. This is a function such as f of x equals 1 over x if x doesn't equal 0, and f of x equals 0 if x does equal 0. This function is certainly not continuous at x equals 0. Simply follow here, going towards -infinity, following here we're going towards +infinity. Those limits do not exist. Forget even being equal to the number 0. Now as practice, I want you to find the number a that makes the following function continuous. Pause your video to work on this. What you're trying to do is find the correct slope of a that makes this function a continuous function. Try that now. So what I've drawn is a picture here to illustrate what's going on. As we choose different values for the slope, the line will look like one of these orange lines, or it might look like this red line, which is the line that makes this function continuous at x equals 1. You see, when x is greater than 1, this function 6x. It's already continuous, right? When x is strictly less than 1, the function's ax plus 4. That piece is continuous. What we need to do is make sure these pieces line up at x equals 1. There's only one slope that will do that. That answer is when a equals 2. 2x plus 4, right? If x is 1, then 2 times 1 plus 4 is 6, and 6x, right, becomes 6 times 1, which is 6. These two functions will have the same value now when x is equal to 1.